Okay, so we're starting with topic 3 in probability, Math 30-2, mutually exclusive events using the addition rule. So our goal is to understand and solve problems that involve mutually exclusive and non-mutually exclusive events. And of course, as part of that, understanding what that means and what those are. So let's explore what is the probability of mutually exclusive and non-mutually exclusive events. So we're going to start with a deck of cards. Jared has a standard deck of 52 playing cards. And we're going to answer the following questions. We're going to consider the following probabilities. What is the probability of Jared picking an ace? So we have to look here. If we highlight our aces, we have 4 aces out of the total 52. Okay, so the probability of Jared picking an ace out of this standard deck is 4 out of 52, which is equal to 1 out of 13. You can convert that to a decimal if you want, but for the sake of what we're going to do, we're going to leave it in fractions. We now want the probability of Jared picking a face card. Well, looking over here, we have 12 face cards in that deck of 52. So the probability of Jared picking a face card, which we'll call F, is 12 out of 52. And we can reduce that to lowest terms. It's 3 out of 13. Okay. And then we want to know what is the probability that Jared draws an ace or a face card. So remembering our terms from set theory. So this is the probability that Jared pulls an ace or a face card. So we're looking for all of the shaded in components. So in total, I have 12 plus 4, which are 16 shaded in items. So that would be 16 out of 52. And if I reduce those, dividing the top and the bottom by 4, I get 4 out of 13. Okay? It says, can you develop a formula in which you use the probabilities in A or B to get the probability in C? Well, if I take 1 out of 13 plus 3 out of 13 and add them together, I will get 4 out of 13. Why does this formula work? Well, because there's no overlap, right? It's either an ace or a face card. So I'm not going to have any duplications if you're thinking about our Venn diagrams, right? So if you just take those equal parts or those separate parts and add them together, it should give us that answer, okay? And so let's look at, this is the formula for the probability of mutually exclusive events. And we can draw a Venn diagram to represent this scenario. So if we have our Venn diagram, our universal set is 52. In there we have a circle that has the aces, which has 4, and the face cards, which are 12, right? 1, 2, 3 times 12. These sets would be disjoint. So when the sets are disjoint, they are mutually exclusive. There is no overlap, okay? Mutually exclusive events are 2 or more sets that have no elements in common. So because there's no overlap and there's no element, that means they're disjoint, and they would be mutually exclusive events, okay? Now, what does that make us think for non-mutually exclusive events? Well, non-mutually exclusive events, let's consider the following probabilities. So, thinking about that same deck of cards, the probability of Jared picking an ace. So, picking an ace, we already know it's 4 out of 52, which is 1 out of 13. Did that already. Find the probability of Jared picking a red card. So now we've got a different restriction there. Here we were getting an ace. Now we're looking for a red card. So the probability of a red card, well, that is 26 out of 52 are red, or 1/2. Okay? Now we want to know what is the probability of Jared picking an ace, or a red card. So again, we're using the word or. So let's map this out. So the probability of a ace or a red card. Now, the thing is if we go take a look at our cards, so we're going to scroll back, and we now look at, we're going to shade in the red cards. So shading in the red cards. So I have 26 red cards. And then I have 2 black cards that meet the criteria of the ace. So 26 plus 2 will give me 28. So I have 28 out of 52 that are either an ace or a red card, or both, because there's overlap, right? So when I reduce that, I get 7 out of 13. Now, can we use the formula we used before, the one we used up there in number 2 at the top, to work? Well, no, it's not going to work because we have overlap. So thinking back to our set theory, it's not going to work because those 2 sets overlap. So we can't count those 2 cards twice. If we just simply added the 1/13 to the 1/2, we would actually get 30 out of 52 because we'd be counting those 2 red aces twice. So can we develop a formula in which you use the probabilities in A and B to get the probability in C? Well, if we add the 452 for A plus the 2652 for the red cards, and then we subtract the 2 cards that overlap, the 2 red aces. So these are the red aces. They fall under both categories. We'll get 28 out of 52, which is equal to 7 out of 13. So what we're subtracting here is we subtract the overlap. And we have to do that, otherwise we're counting it twice, and we don't want that. So this formula for probability of non-mutually exclusive events, we can show with a Venn diagram. So if we have our Venn diagram for this example, we have our universal set, which has 52, and in it we have red and we have aces. Well, in the aces, I'm going to have 2 here, 2 here, and for my red cards, I will have, that are not aces, I have 24. So if I add all those together, I get the 28 out of 52. Non-mutually exclusive events are 2 or more sets that have 1 or more elements in common. So basically, non-mutually exclusive events have overlap. Okay? So we have this little section right in here, which is our overlap. Alrighty. And it does have a bearing on our numbers. So this is why we do set theory before we do probability, so we can understand these relationships. Okay, looking at this. Mutually exclusive events are 2 or more sets that have no elements in common. They can be represented, so sorry, I just want to highlight that. They have no elements in common. 2 or more sets, no elements in common. They can be represented by a Venn diagram, by disjoint sets, and the probability that A or event B will occur is represented by the following formula. So basically, we just add the 2 probabilities together. Non-mutually exclusive events have 1 or more element in common, and they can be represented by a Venn diagram by intersecting sets. So the probability that A or B will occur is represented by this formula. And what we have to do is, here we're subtracting the overlap. So we don't count those items twice. All right? And that is the basis for non-mutually exclusive events. Okay? So let's do some practice with this. Classify the events as mutually exclusive or non-mutually exclusive. And sometimes we might draw a Venn diagram to help us sort it out. So here, rolling an even number or a prime number on a 6-sided die. So let's list. We have even numbers are 2, 4, and 6, right? Now, prime numbers are 2, 3, and 5. Now, if we were to sketch those out into a Venn diagram, I'm going to draw it a little bit bigger because I want to be able to show you what's going on. So this is our Venn diagram. If this is my even and this is my prime, I have 2 there, 4 and 6 here, and 3 and 5 here. So in this case, I do have overlap. So that would make this non-mutually exclusive because there's overlap. And remember, in case we forgot, prime numbers are numbers that have only 2 factors, itself and 1. We should know that in Math 30-2. Okay, let's look at our next example. Scoring a goal or winning a game when playing hockey. Now, there are times we score goals and times we win the game. And sometimes we score some goals and we don't win, and sometimes we score goals and we do win. Sometimes we win and we haven't scored a single goal. So there is overlap between these two sets. So this would make this be another example of a non-mutually exclusive event. Okay? Purchasing an edible gift or a CD gift. Well, I don't know about you, but I don't eat CDs. So this would be edible and these would be the CDs. There is no overlap, so these are mutually exclusive. There is no overlap. So if we were doing those, we would just simply add them together. Whereas the first two, A and B, we would have to subtract the overlap. Selecting one card from a standard deck of 52 that is either a spade or a face card. Well, the question we ask ourselves is, are there spades that are face cards? Why, yes, there are. So here's our face cards, here's our spades. So here I'm going to have ace to 10. Here I'll have jack, queen, king. Oh, sorry, I did it wrong. But I would have the jack, queen, king of spades, right? And here I would have all the rest, other suits. And here I would have the rest of the spades. I got a little silly there. So we do have overlap because the jack, queen, king of spades are face cards and they are spades. So this would be not mutually exclusive. Okay? So if all else fails, and it would not be a bad thing to have little sketches of circles all over your papers just to help you figure those out. Okay? So let's take a look. And remember too, if I go too fast, you can always pause the video to take a pic or to look at the picture and to sketch those in your notes. Probability of mutually exclusive and non-mutually exclusive events. A card is drawn from a deck of 52 cards. Determine whether or not the following events are mutually exclusive and find the probability. So the nice thing about this is we've drawn out the whole deck, so we can do some highlighting to sort it out. So let's highlight drawing either a heart. So those are all my hearts. I'm shading them in green. Or a face club. So let's shade that face club. The face clubs are up here. Now there's no overlap, is there? So they aren't they are mutually exclusive. So the probability of drawing a heart or a face club is equal to, well, in total I have 13 hearts and 3 clubs that are face cards. So it's 16 out of 52, and it is 4 out of 13. I also could have added them together, remember, because I could have 13 out of 52 for my hearts, plus 3 out of 52 for my clubs, get my 16 out of 52, and then reduce it. Either way you do it, right? Might as well collect them all. Drawing a red card or an even card. So the probability of a red or even card. So let's think about that. Now I can shade them or I can just think about it. For red cards, I have 26 out of 52 red cards. And for even cards, I also have, well, what do I have for even cards? I have 1, 2, 3, 4, 8, 12, 16, 20, and then I have my face cards. Okay, so I don't really count my face cards in that. Okay, so I have 20 even cards, but there's overlap, isn't there? If I look at this, I also have red cards that are even cards because I've got those two, those two, those two, those two, and those two. So I've got 2, 4, 6, 8, 10 even cards. So I have to subtract those because there is overlap. So minus 10 out of 52. So what I'm doing here is I am subtracting the overlap. Okay, you have to do that. So let's add up our totals. 26 plus 20 minus 10 is 36 out of 52, which reduces to 9 out of 13. Okay, so it's important to kind of take a look at what your cards are and where they might possibly overlap. Okay. Let's keep doing more examples because that's how we learn. So here we have Jen rolls 2 4-sided dice. So 4-sided dice go from 1 to 4. Draw a sample space that includes the sum of the 2 dice, not rice, but the dice rolled. So we're going to create our sample space here. Okay, so here we're going to have 1, 2, 3, 4, and down here 1, 2, 3, 4, and then we're just going to add them. So I'll get 2, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, 7, and 5, 6, 7, 8. So those are all my sums. Now we have our sample space, so it's nice to have that. Determine the probability that Jennifer will roll a sum that is either a 6 or an odd number. So let's highlight those. So we have 6s here, 6, 6, 6, and then we can also highlight our odd numbers. So I have 7's an odd number, 5 is an odd number, so we'll highlight all of the 5s and all of the 7s, and 3 is an odd number. Okay, now we know all of our possible answers. So the possibility of rolling a 6 or an odd is equal to, well, for the 6, I have 3 out of 16, because there's 16 in total. And for the odd, I have 8 out of 16. Okay? And you can see 6 is not an odd number, so there is no overlap. So I can just add those, and I'll get 11 out of 16. Okay? The other way I could do it is just by highlighting them and counting them up. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 out of 16. So whether you write that out as an addition or you just add them up, it's totally fine. Okay? But the big thing to note is there's no overlap. Making a decision based on probability. Now, Reed's mother buys a new washer and dryer set with a 1-year warranty. She has the option of buying a 3-year extended warranty for $450. Reed, what a good son, researches the repair statistics for this washer and dryer set and finds the following data. So he finds that the probability of repair within 4 years for a washer is 22%. For a dryer is 13%. And the average repair cost for the washer is $400. Average repair cost for the dryer is $300. And if both of them break, the average repair cost is $700. So what we want to figure out is what, it says if there is a 68% that neither appliance will need to repair within 4 years, are these events mutually exclusive? So we have to sketch a Venn diagram to figure that out. So we have the washer and the dryer. Now the total is 68%. Right? So we expect the washer and the dryer to add up to 68%. The washer, or will not eat. No, this will be 68% out here. So remember, this has to add up to 100%. So that means the washer and dryer have to add up to 100 minus 68, right? So 100 minus 68 equals 32%. Now, take a look at this. If I take my 22% for my washer and my 13% for my dryer, they add up to 22 plus 13 is 35%. So they are not mutually exclusive. Because this 35 is greater than the 32%, that means we've got an overlap, and the overlap will be the difference, so it'll be 3%. So the total washer is 22%, so that means that this has to be 19, because 19 plus 3 is 22%, and the total dryer is 13 minus 3 is 13, so we minus the 3, and it'll be 10%. 10 plus 3 equals 13. So the chance that both will break is 3%. Okay? So pretty low risk that they will both break. Higher chance that the washer will break, and it costs a little more. All right. Now, let's continue. Determine the probability that at least one appliance will need repair within 4 years. Well, probability of the washer or the dryer will need repair. Well, we know, because we figured it out up here, that is the probability, right? It's 0.32 or 32%, right? Based on that information, would you recommend she buy the extended warranty? So I guess this is just really up to you in terms of whether or not you feel that they should. You can do a cost analysis, complete that table. In terms of buying that extended warranty for $450, it might be worth it to get it so that you don't have to pay if it needs a repair within 4 years. It really depends on if you think that the odds are in your favor. So with 32%, I don't know, it might be worth it. Or you might say, you know what, if I just take good care, it won't. Now you can do a cost analysis. The probability of needing the repair for only the washer is 22%. Only the dryer is 13%. And both needing repair is 3%. So it's just a matter of how much you would save. Well, it would cost you $50. Cost, right? Because you're paying $450 for that warranty. Here, this would cost $150. That would be a cost. However, if both broke, 750 minus 700 minus the 450, you would save $250. So it's really hedging your bets, playing your odds, and then justifying your decision. I think you have to kind of decide for yourself which decision you would make. Okay, I'm not gonna make that decision for you. Some people know, like I'll tell you this: when I'm buying games for my kid, they always want to sell me that extended warranty. I say basically, he breaks it, he's paying for the next version, so hopefully he'll take good care of it. But then there's some things that I will buy the extended warranty for because I know I've had them before and I've had the experience. We bought a Chromebook for my son a few years ago, and I was glad we had that standard warranty, and I was glad we had it, and that it broke within the first year, so that when we got the second Chromebook or laptop we got for him, we actually bought the extended warranty because we'd had the experience of the first one breaking. So sometimes it's just a matter of your own personal experience. Reed did research here, and you just kind of want to look at it and say, well, what are my chances, right? In terms of moving forward. Okay. All right. So mutually exclusive events are two or more sets that have no elements in common. We call them disjoint sets, right? So that's a term from set theory. So they have no elements in common. You can see there's no overlap. No overlap. Okay. It's the big tip off. And we can use that addition formula to solve it. Non-mutually exclusive events do have one or more elements in common. So we do have overlap, and there is overlap in this situation. So there's some criteria that meets both of our situations. And when we're dealing with these, we have to subtract the overlap, okay? So that is what we're subtracting, our overlap, okay? When two events are mutually exclusive, both formulas are equivalent, since this equals 0. That means there's no overlap, right? This means no overlap. Okay. Now, moving on, we're going to be talking about dependent and independent events. So you're going to have to find a way to keep what we learned today about mutually exclusive and non-mutually exclusive events different from dependent and independent events, because they are totally different concepts. So I'm just prepping you for that. So really take the time. That's why I decided to just do the one lesson today. So we just focus on this. Oops. And tomorrow we will look at the next situation. I want to get back to the right page. It's important for you guys, sorry, it's going to let me scroll, to really take a look at what this is talking about.